Section 2.1 is on page 121. Talks about sets, and start with the definition. What a set is. A set is an unordered collection of distinct objects called elements or members of the set A. A set is said to contain its elements. We write A belongs or a member of A to denote that A is an element of this set. That's a notation for one element. The notation A does not belong to A denotes that A is not an element in this set. Now, with set comes set builder notation. That's normally what we use. Another way to describe a set is to use the set builder notation. And set builder notation looks like, well, we characterize all those elements in the set by stating the property or properties they must have to be members. The general form, if set has those parentheses, this is the variable in question, this is the condition such that, and this is really what you want to impose on these variables. And you read it, the set of all x such that x has property p. For instance, we have an example. The set O of all odd positive integers less than 10 can be written as, this is the variable x, such that x is an odd positive integer less than 10. You could write it slightly different. You could say x belongs to the positive integers, right? X is odd and less than 10. That describes the same set. Keep in mind that when we write just x, we're assuming that the domain would be integers. If it's anything other than that, we would have to specify. So in the book they use that. If they say x and they will say anything, they're talking about integers specifically. So we're looking at problem number 2. Let me check the page. Page 131 in our book. Use set builder notation to describe the set. Again, there are many ways you could describe it. You could say this is the set x such that x is a multiple of 3 and x is between 0 and 12. So when you include them, you start with 0, 3, 6, 9, and 12. There are other ways you could write this that will work. That's not the only way you could write it. If we look at this set, again, remember, by saying x, if I don't specify anything about x, that means it's integers. So here I could say x is between -3 and +3. Here I could say this is the set x such that x is the letter M, N, O, or P. Now, when we talk about sets, probably, especially when we start talking about included and non-included, for each of these intervals, list all the elements or explain why is it empty. Now, empty means there's nothing in it. So, in A, part A that is, when you put a bracket on A and you're using interval notation, this set consists of one element only, and that is A. Here, this is the empty set. Now empty, the notation for empty is this. It's like there's nothing there. And the reason for that, you cannot have both a number that is bigger than, greater than, and at the same time less than, because that indicates it's not included. So you can't have both of those at the same time. Similarly here, the same thing. You can't have a number that's less than A and equals to A. And this set does not include A at all, so that's also empty. Here when they say AB, so this is not including A, not including B, and they say A is less than B, that's also empty because there's nothing there. And if they include both ends, you would think an interval notation on a number line, or let's use that one. If that's set A, and that's set B. Well, it's all the elements between A and B, but they tell you here that A is bigger than B. So that can't happen. You can't have a value here. If A was less than B or less than or equal, that will work. But to have A be bigger than B, that doesn't make sense. So this set is empty as well. Now, this is the notation that they use. Natural numbers, they use capital N. Integers, they use Z. Now, the positive indicates only positive integers. Q are all the rational numbers. These are numbers that you could write as a fraction in which the top and the bottom are integers except the denominator cannot be 0. Real numbers consist of rationals and irrational numbers. Are positive, of course, these are all the positive real numbers, and C is the complex, and you could also see it like this. Those are all the complex numbers, A plus BI. Definition: two sets are equal if and only if they have the same elements. Therefore, if A and B are sets, then A and B are equal if and only if every element that's in A is automatically in B, if and only if, and every element in B it's automatically in A. We write A equal B if A and B are equal sets. Now the empty set, I already explained what that is, but here's a good explanation because you need to understand the difference between this and this. And I like the example they have, which is why I copied it here. There is a special set with no elements. This set is called the empty set, or null set. Think of it as an empty folder. And we denote it by a 0 and a slash in between. If this is how you write 0, you should stop doing that. That's the empty set. The empty set can also be denoted by simply saying there's nothing there. That is, we represent the empty set with a pair of braces that encloses all the elements in the set. Often, a set of elements with certain properties turn out to be the null set. For instance, the set of all positive integers that are greater than their squares is the null set. A set with one element is called singleton set. Now again, we're not going to really be focused on this, but sometimes they use that language. A common error is to confuse the empty set with, if you put anything in there, including that notation, now you're saying we have the empty set, the empty folder in that set. So for example, the single element of the set, the empty set, is empty set itself. A useful analogy for remembering this difference is to think of a folder in a computer. So if you made a folder in a computer and you create call it set A, you click on it, it's empty. If you put another folder in it that's empty, now that set has an empty, that folder has an empty folder and it's no longer empty. Use the analog for remembering this difference. So the empty set can be thought of as a folder, and the set consists of just another empty set inside it, so it's no longer empty. It has an empty, so it's a folder within a folder and there's nothing in them. Venn diagram, I'm going to demonstrate with a graph. So the universal normally is in a rectangle, and the sets, if they have something in common, if they're disjoint, you represent them differently. I'm sure you've seen it. I will go over some examples with that. I just need one more setup before I could go on. A set A is a subset of B, and B is a superset of A if and only if every element of A is also an element of B. We use the notation A is a subset. So this indicates that this is an element. This indicates that this is a subset. All the elements in this set are also in this set. And you could use the notation forward or backward. That indicates the same thing. So I want to look next at problem number 14 and kind of start this analogy and how it works. Okay, I did move it right there. All right. So anytime you want to sketch a Venn diagram, probably you should create, not necessarily you have to do that, but normally we do use Venn diagram to illustrate the subset of odd integers. How many of those do I need? Odd integers set not exceeding 10. Odd integers not exceeding 10. Okay, actually I didn't need the other one, but let's just put it there. So use Venn diagram to illustrate the subset, a subset of odd integers. Odd integers would be 1, 3, 5, 7, and 9. Now you could put it right there. You could say not exceeding 10. So what are we missing? 2, 4, 6, 8, and 10. Of course, you don't need the rectangle in this case. You could put it there if you want, or you could just take it out. That's not an issue. You could also do this if you like. That works as well. Either way, that's the same thing. We want to draw another Venn diagram. Let me see here what we need. Oops. We need, oh, of course we're going to have one of those, but let's see what we need. Use Venn diagram to illustrate the relationship. A is a subset of B. Okay, so A is inside of B. That's for sure. So there is set A and there is B. And B is a subset of, so I need another one. That's kind of like set C. Normally this is the universal, this is everything that there is. 18, another example on Venn diagram, again a rectangle. Use Venn diagram to show, and let me see what we have here. We have, to illustrate the relation, A is a subset of B and A is a subset of C. So we have two sets and they have a set in common, which is A. So A is a subset of C and A is a subset of B, and this is the universal. So again, the idea is not that challenging, but it's very useful, especially when you have a lot of sets. Now, get to the next problem. Okay, we have 6, so we're running back really quick. For each of these pairs of sets, determine whether the first is a subset of the second. The second is a subset of the first. Neither is a subset of each other. Set A states the set of people who speak English. The set of people who speak English with an Australian accent. Well, the second condition imposes an extra requirement. So the second are the people that speak English with an accent, in this case Australian. So clearly the second set is a subset of the first, but not vice versa. So people that speak English would be the general. People that speak English with an Australian accent, that's a subset of the first set. Second one, the set of fruits, the set of citrus fruits. Well, citrus is more conditional. So fruits is the whole set, and citrus is a subset of that citrus fruit. C, the set of students studying discrete math, the set of students studying data structure. Well, this could well be students studying discrete math, but not data structure, right? For, you know, if you're studying a specific type of mathematics in which you don't have to take data structure, you just have to take discrete math, right? And you don't have to be in both, at least not in the same year, maybe a different year, maybe not the same semester, you know. So this, neither set is a subset of the other. That could be the case here. It depends. Let me fix the problem really quick. Okay, before this definition, there's a definition right there. Here, for every set S, the empty set is in any set, and any set is a subset of itself. To show that two sets are equal, this is something we're going to prove. Two sets A and B are equal. you show that all the elements in A are in B, which means A is a subset of B, and you show that every element in B is a subset of A. That shows that B is a subset of A, or belongs, I should say. So here, problem number 8 says, suppose A is 2, 4, 6, B is 2, 6, C is 2, 4, 6, and D is 4, 6, 8. So we notice those two elements are right there. Those two elements are right there and right there. But 8 is not in A and 2 is not in D. So first we say each set is a subset of itself. That's traditional, that's normal. So A is a subset of A, B is a subset of B, C is a subset, oops, wrong notation. C is a subset of C, and D is a subset of D. So now, also we know that B is a subset of A. We also know that C is a subset of A, and we also know that C is a subset of D, we said. There you go. Now, let S be a set. If there are exactly n distinct elements in A, where n is a non-negative integer, we say S is finite. And n is the cardinality of S. The cardinality of S is denoted by like an absolute value, or if you're thinking of vectors, the magnitude. So if I wanted to look at number 22, that's a bit trickier than the traditional. So just think of what we talked about, folders and all of that. It says, what is the cardinality of each set? Well, A, it's 0 because there's nothing there. It's an empty set. B, it's a folder, but within that folder, we do have a folder. So that's one set. There's one folder inside. On C, we have 2 in there. And on D, we have 2. 1, 2, 3 in them. So again, think of a computer. If you open the system, what do you see? You see how many folders? You see a folder, you see 2, you see 3 folders. Now within this folders there are 2, but you only see 3 when you open it. Here you see one folder and you see another folder that's empty, but they're individual. So definition 7 talks about the order n tuple is the order collections of A sub 1 as the first element, A sub 2 as the second, and so on. And we're going to do examples on each. And let A and B be the sets. The Cartesian product of A and B, denoted by A, it's like really cross B, is the set of all other pairs where A belongs in the first and B belongs in the second. So all the elements A and B such that A is in the first and B is in the second. So let's look at the first example. I took the problem in the book because I couldn't find one in the homework that's straightforward. I saw one that's complex. We're going to do it after. So if I wanted to really do this example, I would say, well, let's see. We have 1 and A, 1 and B, 1 and C. We also have 2 and A, 2 and B, 2 and C. And if I look at number 30, what is the Cartesian product A cross B, where A is the set of courses offered by the mathematics department at a university, that's A, courses. B is the set of math professors at the university. So here, by definition, if we talk about the set C for courses, P for professors. This will be the element of sets that are the possible teaching assignments for mathematics department. Which teacher or which course is taught by which professor. Now, 28, we want to look at showing. Show that if A is a subset of C and B is a subset of D, then A cross B is a subset of C cross D. Now, how would you do such a proof? Well, or a show. We need to show that every element in A cross B is also an element of C cross D. Well, by definition, if I look at A cross B, these would be all the pairs AB where A belongs to A and B belongs to B. Now, because A is a subset of C, we know that A is a member of C as well. Similarly, if B belongs to B, we know that B belongs to D as well. Therefore, AB belongs to C cross D. And here we're talking about all the combinations of A and B. Since you're making it general, not specific, it works that way with ease. Now the last set is number 30. When you cube a set, it has only one set of elements, so that would be the triplets A, since there's only one element in it. But here, if you look at that, well, we have two of those. Here we would say, well, that's 0, 0, 0, 0, 0, A. Start with A and start moving A inwards. 0, A, 0, and A, 0, 0. You also start with, oops, that's 0 out of mic. Let me clean that one up. You could also start with A, 0. No, I missed the two A's here. Let me start. So we start with A. Then you start with 0, A, and A, 0, A, and A, 0. And the last one would be A, 1, 2, 3, 4, 5, 6, 7, 8 of them. That's true. And that concludes this section.